This is going to correspond to Chapter 12 in our chemistry books. This is 100% stolen PowerPoint from the internet. I don't have the person who created it, but I appreciate them creating it. So let's look at ionization energy. Energy required to remove 1 mole of electrons from 1 mole of gaseous atoms, which we covered in Chapter 11. From the last chapter, we talked about trends in ionization energy. And metals tend to lose electrons have a lowest ionization energy. Nonmetals gain electrons and have the highest ionization energy. So which element has the highest ionization energy? That would be fluorine. Which one has the lowest would be down the bottom left-hand corner. Electronegativity measures the attraction of an atom for electrons. And this is just showing an equal sharing of electrons. Here's the nucleus of 2 atoms that are side by side, so equal sharing. This is unequal sharing, so we have a center that's slightly negative and a center that's slightly positive, and then we have one that's an ionic bond where we actually have a transfer of an electron. And that's what we have. So this one has such a much higher electronegative value, it actually takes the electron and they're held together by a static charge. So the electronegativity trend, francium has the lowest and fluorine has the highest affinity. So let's look at some examples of electronegativity. We're going to draw in the bonding electrons, and this is the example that we have to go with hydrogen and fluorine. The bonding electrons are going to be closer to fluorine because fluorine has a higher electronegative value than what hydrogen does. We're going to look at 2 examples, so I'll just give you a minute to look those up on the periodic table, decide which one has the greater electronegative value, so which one's going to keep the bonding electrons more of the time. And if you look that up, you'll notice that bromine is going to have the higher electronegative value, so it's going to have the electrons closer to it, and chlorine in the other pair. This one says to arrange from lowest to highest the electronegative values, and you can take time to look at your periodic table, or you can pause the video. So when we put them in proper order, this is what it would look like with indium, antimony, selenium, and fluorine being the largest electronegative value. Again, another one to look at, going from smallest to largest. If you need to, pause the video while you try to figure the answer out. The answer then would be in this order with francium, zinc, gallium, germanium, and phosphorus being the largest or having the highest electronegative value. Which has a greater electronegativity, a metal or a nonmetal? Definitely a nonmetal. Which is more electronegative, copper or sulfur, bromine or gallium? So we'll have to decide which one's a metal and which one's a nonmetal. So since nonmetals have a higher electronegative value, sulfur has a higher electronegative value than copper, bromine has a higher one than gallium. Polarity is the separation of charges, and we're going to use the symbol for delta, and it means partial. So for example, copper and oxygen has a higher electronegative value than copper, so oxygen will keep the bonding electrons in its orbitals most of the time, making it slightly negative, and that leaves copper being slightly positive. So there's a polar attraction between those two. And this is kind of what it would look like sketched out. Here's their nuclei that are in the center here, and the electron clouds. We see that oxygen is going to have the electrons more of the time and be slightly negative, and copper is going to be slightly positive because oxygen is bullying copper and taking the electrons more of the time. So what causes this polarity? It's an unequal attraction toward the electrons. Somebody's got to be stronger. In this case, it's oxygen. Polar molecules have distinguishable sides or opposite ends, just like a polar region would. You can identify the top and bottom or left and right sides, and they're asymmetrical. So when we look at these examples, there's unequal sharing here, and there's a shift because of the unequal sharing and pull toward those electrons. Nonpolar molecules, on the other hand, are symmetrical. There's an equal distribution of charge, and because of that, there's not a positive or a negative end. And we see that in this dumbbell shape here, which would be any diatomic molecule. Boron, we'll talk about shapes later in this chapter, and this is called a trigonal planar shape, and this planar shape allows it to have equal pull on the electrons. So there's equal sharing, no positive or negative end. and the same thing with the tetrahedral shape of the carbon tetrachloride. Everything is the same around the central part. Attraction between atoms allows for chemical bonding to occur. So electrostatic attraction is when opposites attract, and you have positives and negatives that are attracted to each other. An atom's protons are attracted to another atom's electron. We have to decide what kind of bonds we're dealing with. So to help us determine that, we have to look at the electronegative value of the different atoms. And we also need to look at the change in the electronegative value between the atoms involved. So this is a chart similar to one that's in your textbook that can show you that. Here we have fluorine, which has the highest electronegative value, and also kind of gives you a 3D structure to look at, seeing that it would stick up higher than the rest of them. While we have over here on this side with the lower ones that tend to be a little bit flatter on the picture to help represent the differences in electronegative values. So the bond types that this particular PowerPoint is going to address are the ionic, the covalent, and then the metallic bonds. Let's look at ionic bonds first. This is where electrons are actually transferred from a metal to a nonmetal, and that allows them to actually have a charge of a positive one or a minus one, depending on how many electrons are transferred. Sodium gave up one electron for the chlorine, so it becomes -1, and sodium +1. Electrostatic attraction is what then holds them together. The bonds that have a bond difference of the electronegative value being 1.7 or greater will cause ionic bonding. Shows you a couple of examples. Difference between lithium and oxygen is about 2.5. So we have an ionic bond. So acids, bases, and salts are considered ionic compounds based on their electronegative differences. Ionic substances tend to have very strong bonds. They have high melting points, and they are water soluble, so they will dissociate in water. When they dissociate in water, they conduct electricity as liquids in a solution, and they definitely have a crystalline form. So on this slide, you'll see that if we have just distilled water with no ions in it, that an electric current cannot flow through that. And you see that if we just have it in, this is crystalline salt, so there's no liquid water in it, and we don't have an electric flow through that. However, if you put together the distilled water and the ions that are formed when you put sodium and chlorine together, you actually will enable it to have electric flow through it. So it has to have a solution of ions in the distilled water in order for the electric current to flow through it. Covalent bonds, on the other hand, are formed from two or more atoms sharing an electron pair. And here we have water with a covalent bond here with sharing a covalent bond here. And we would write this, we'll learn later in the chapter how to write the structures correctly, but that's what the Lewis dot structure would look like. Covalent bonds usually formed by two nonmetals, which means that they have a similar electronegative value, and the electrostatic attraction between the atoms holds it together. We consider this covalent bond between two or more atoms, making it into a molecule instead of an ionic compound. So covalently bonded atoms form molecules. Here's the electronegative chart again. If you notice carbon and silicon, for example, if you look at the difference in their electronegative values, it's only 0.7. Since it's so much lower than 1.7, it's going to be a bond that is sharing the electrons instead of transferring the electrons. Fluorine and fluorine, if we have the diatomic molecule, 4 minus 4 is going to be 0, so there's no difference in electronegative values. So that molecule is also going to have a covalent bond. Characteristics of covalent substances: they tend to have low melting points, they don't conduct electricity, and they tend to be brittle. So the types of covalent bonds are nonpolar covalent and polar covalent bonds. Nonpolar covalent has equal sharing of electrons, and we see these in the diatomics: chlorine, hydrogen, bromine, iodine, just for example. So why does that happen? Why is there a nonpolar covalent? Why is there equal sharing? The reason for that is the difference or delta change in electronegative values is 0. Polar covalent is an unequal sharing. So anytime you have a difference in electronegative values at all, and it's a covalent bond, it will be a polar covalent bond, and you'll see an unequal sharing of electrons. In H2S, which attracts electrons more That would be the sulfur because it has a higher electronegative value. What is the approximate change in the electronegative values? And it's about 0.3. Last thing we're going to cover in this section are metallic bonds. These are characterized by free moving electrons. It's called the electron C model, and this is found in metals, and it's a very strong bond. So these are positively charged ions and electrons that are floating throughout it because of the positively charged ions. And of course, negatives are going to attract positives, positives are going to attract negatives, and this is going to cause it to have this uniform model.